Hello everyone, welcome to this lecture on Lagrange's interpolation formula. I am Dr. Vikrant Yadav, working as an assistant professor in Department of Mathematics, School of CS and AI at SR University, Warangal. In this lecture, we are going to study one of the most important topics in numerical methods, which is Lagrange's interpolation formula. Now, before we directly move to the formula, let me ask you a simple question. What if you are given only a few data points of a function, but you don't know the actual function? For example, you are given values of x and corresponding values of y, but you want to find the value of the function at some other point. So how can we do that? This problem is solved using a technique called interpolation. Interpolation helps us to estimate unknown values, construct a function from given data, and make predictions based on available information. And in today's lecture, we will focus on one of the most powerful and widely used methods, Lagrange's interpolation formula. In this session, we will understand the concept of interpolation, learn the derivation of Lagrange's formula, and solve numerical problems step by step. So by the end of this lecture, you will be able to construct interpolation polynomials confidently, solve exam-based problems easily, and understand how this concept is used in real-life applications. So let's begin it. Alright, let us now move to the motivation and core concept behind Lagrange's interpolation. Okay, why Lagrange's formula is there? First, let us understand why we even need this formula. You might have already studied Newton's forward and backward interpolation formula in the previous lectures. These methods are very useful, but they come with an important distinction. They require the data points to be equally spaced. Okay, now think about this carefully. In real life situations, do we always get equally spaced data? The answer is obviously no. Most of the time, data is collected at irregular intervals and measurements are not uniformly spaced. So, what do we do in such cases? We need a method that works regardless of the spacing, okay? And that is exactly where Lagrange's interpolation formula comes into picture. It works with equal and unequal spacing both. So it is general and flexible method. Now, let us clearly understand the problem. Suppose we are given a set of data points, and that set of data points is this one, x0, y0, first pair of points. This is x1, y1 till xn, yn. Okay, this means we have n plus 1 non-data points. Okay, the total number of non-data points is n plus 1. Each xi has a corresponding value yi. So here you are finding out the value of x, the value of x3 is there, so corresponding value is y3. Okay, so our goal is to construct a polynomial that passes exactly through all these given points. Okay, so here is a very important theoretical result. The result states that for n plus 1 data points, there exists a unique polynomial of degree less than or equal to n. Okay, there exists a unique polynomial of degree less than or equal to n that passes through all these points. Okay, let me repeat this because it is very important for exams. The first point is there exists a unique polynomial, okay, of degree less than equal to n, and it passes through all given data points. That is very important. This is the foundation of interpolation. Okay. Now let us understand the main idea behind Lagrange's method. Instead of directly constructing the polynomial, okay, instead of directly constructing the polynomial, we build it using smaller components called Lagrange's basis polynomials. Okay, there is Lix. They are denoted by this term Lix. Okay, is in the subscript. Each Lix is specially designed such that Lixj equals to 1 if j equals to I. If it is equal to, if I and j are not equal, in that case that will be 0. Okay. Now let us understand this slowly. Take Lix. Okay. When we substitute, I have taken Lix. Okay. When we substitute x equal to xi, okay, then L of this I is having L of xi and it will be 1. Otherwise, if we substitute x equal to xj, then the same quantity is there, Li xj, then it will be 0. Okay, so each basis polynomial behaves like a selector function. It selects only one specific data point and ignores all others. This is a very important point. Let me repeat it again. Each basis polynomial, this Lix, okay, behaves like a selector function. It selects only one specific data point and ignores all others. This is the key idea. Okay, we construct individual polynomials that activate one data point at a time. Okay, so now once we have all these basis polynomials, okay, for all values of I, then we combine them to form the final interpolation polynomial that is given by this px equals to summation I equal to 0 to n yi lix. Okay, let us understand it very carefully and clearly. For each term, yi is the given function value. Okay, yi here is given function's value. Lix ensures that this value contributes correctly. So when you substitute x equal to xk, okay, when I substitute x equal to xk here, all terms become 0 except 1, okay, where I equals to k, okay. So in that case, we'll be getting the value as p of xk equal to yk. This guarantees that the polynomial passes through every data point exactly, okay. Now we come to the advantages of Lagrange's formula. The first advantage is that it works for unequal intervals as well, and this is the biggest advantage. Second is that there is no need to construct a difference table. Okay, it is unlike the Newton's methods. It works with unequal intervals, and there is no need to construct difference tables here. Again, the formula is symmetric in nature, which makes it easier to understand and implement in the programming. Okay. However, there are certain disadvantages as well with this Lagrange's method. First one is if we add a new data point, we need to recompute the entire polynomial from scratch. Okay. This means the polynomial may show large oscillations, especially near the boundaries, and this is known as Runge's phenomenon. Okay, Runge's phenomenon. So we need to be careful when using high degree interpolation. Correct. So in this slide, we have understood why Lagrange's formula is needed, how it overcomes the limitations of Newton's methods. Okay, the idea of basis polynomials we understood here, and how to final interpolation polynomial is constructed. So I hope these points are clear to you. Now let us move to the next slide. All right. Now let us move to the most important slide of this lecture, where we will understand the actual Lagrange's interpolation formula in detail. The general formula for n plus 1 data points is in front of you. Let us start with the general term. We have already seen that the interpolating polynomial is given by p of x equals to summation I equal to 0 to n yi lix. Okay, this means that the polynomial px is constructed as a sum of terms, where each term consists of the function yi, okay, then multiplied by the corresponding basis polynomial, that is Lix. Okay. Now the most important part is how do we define Lix? Okay, that is Lagrange's basis polynomial. The Lagrange's basis polynomial is defined as the product of x this term. Okay, product from j equal to 0 to n, and this is x minus xj divided by xi minus xj. The ith Lagrange's basis polynomial is defined as, I repeat the formula, this is ith Lagrange's basis polynomial defined as product of from j to j equal to 0 to n x minus xj upon xi minus xj, where j is not equal to I. So we exclude the term where I equals to j. Okay. So here we take a product over all j, but we exclude the case when j equal to I. So each Lix is a product of several linear terms. When we substitute x equal to xi, if I substitute here x equal to xi, so numerator and denominator become equal, which cancels exactly with the denominator. Okay, numerator will be cancelled with the denominator, and Lixi will be, let me write here, Lixi will be equal to 1. Now if I substitute x equal to, sorry, x equal to xj, in that case numerator becomes xj minus xj, and that will give you Li Li xj equal to 0. Okay, this confirms the special property that we discussed earlier in the last slide. Now let us look at some important properties of Lix function polynomial, sorry. Okay, first, each Lix is a polynomial of degree n. Okay, it's a polynomial of degree n because it is the product of n linear factors. Again, Lixi equals to 1 and Li xj where is equal to 0 for j not equal to I. Correct? This ensures correct interpolation. Also, this term summation I equal to 0 to n Lix equals to 1 for all x. This is a very this is very important identity. It tells us that the basis polynomials form a partition of unity. Okay, and the last one, that is the polynomial Lix are linearly independent. This means no polynomial can be written as a combination of others, and each contributes uniquely to the final result. Okay, then now let us simplify things with a concrete case explicit formula for 3 points. Here this is n equal to 3, number of points equals to 3. Okay, suppose we have 3 data points, say x naught, y naught, x1, y1, x2, y2. These are the 3 data points. Now the interpolating polynomial px will be equal to this expression on the right hand side, that is y naught into x minus x1 into x minus x2 upon x naught minus x1 x naught minus x2. Okay, plus y1 into x minus x naught into x minus x2 upon x1 minus x naught into x1 minus x2. So okay, similarly the third term is there. This is your first term I am writing y naught. This will be L0x. Okay, this will be L0x. Correct? The second term will be y1 L1x. Third term will be y2 L2x. Okay, these are the terms are being written. This formula is really important for your exams. Okay, each term corresponds to one data point. Each term become one at its own point and zero at others. So together they ensure that the polynomial passes through all 3 points. Now let us briefly discuss the error involved in interpolation. The error is given by this formula e of x equal to this expression that you can see on the screen. Okay, here this symbol lies between the minimum and maximum of the given data points. Okay, this lies between minimum and maximum of the given data points. And this function f of derivative of the order n plus 1 is n plus 1 derivative of the function. Okay, what does this mean? The error depends on the smoothness of the function, the number of data points, and the distance of x from the given points. Okay, error becomes 0 at the given data points. Actually, this error tends to 0 as x tends to xi. Okay, and error decreases as we use more points. That is very clear from here. But increasing degree too much can cause instability. Okay, so these are the main points here about Lagrange's interpolation formula. Now let us move to the next slide. So right, now let us move to our first solved example, which is very important from an exam point of view. We are given the data that x equals to 0 1, 3, and y equals to 2, 3, 7. Okay, and we are asked to find out the value of the function at the point x equal to 2. This is p2, or function's value, y's value at 2. That means we need to find the value of the function at the point x equal to 2 using the given data points only. So let us examine it. This x0 is 0 here, x1 is 1, x2 is 3, y0 is 2, y1 is 3, y2 is 7. Okay. Since we have 3 data points, we will use Lagrange's interpolation for 3 points. Okay. Our first step is to compute the basis polynomials at x equal to 2. Okay. So here I have calculated L02, L12 and L22. Okay. L02 here is 2 minus 1, that is x minus x0. Okay. X minus x1. So it is, let me write the formula here. This is x minus x0 upon, not sorry, x1. This will be x0 minus x1. Okay, so this is the case here. Okay, similarly, for the second value 2 minus 3, this value is written as x minus x2 upon x0 minus x2. Okay, so the product comes out as minus 1 by 3. So our first basis polynomial's value at the point x equal to 2 is 1 by 3, minus 1 by 3. Similarly, L12 you can calculate, and that value will come out as 1. And same way, the value of L2 at the point 2 is again 1 by 3. Okay. So now we have used, just now we have the values of L02, L12, okay, and L22. So we use the formula, that is Lagrange's formula for this function, that is equal to P2. Okay, this is actually, let me cross it. P2 will be equal to y naught L02 plus y1 L12 plus y2 L22. Okay, this is actually L22. Okay, now you are supposed to put the values of y naught from this table, that is equal to 2 here. Okay, this value will be taken here, and then L02 value are having from here, that is minus 1 by 3. This is y1 is 3, L12 is, you calculated just now, equal to 1, L by 2 is your 7. Okay, L22 is 1 by 3. You just substitute the values here, and you'll be getting the value as 14 by 3, final value. For at the point x equal to 2, the value of the function is coming out to be 14 by 3. That is approximately equal to 4.667. Okay, this is 4.667. So the estimated value of the function at the point x equal to 2, you can say it as 4.667. In this slide, we show that how we can estimate unknown values using interpolation. Okay. So now let us move to solve example 2, where we are given 4 data points. Okay. This question is slightly more advanced and very important for exams. Okay. So let us try to understand the problem. We are given data x equal to 1, 3, 6, 8 and y equal to 3, 9, 18, and 24. And we are asked to find the value of this function at the point x equal to 5. Okay, that means we will need to estimate the value of the function at x equal to 5 only. So let us try to understand the data very carefully. Here x naught is 1, x1 is 3, x2 is 6, x3 is 8. Okay, and corresponding values of y are y0 equal to 3, y1 equal to 9, y2 equal to 18, y3 equal to 24. Since we have 4 data points, we will construct a polynomial of degree less than or equal to 3. Okay. Now, before solving, listen very carefully. Instead of writing full L0 this L0 x or L1x, okay, before calculating these expressions, or you can say L2x, this type of expression that is basis polynomials you need to calculate. But just think carefully and listen very carefully. Okay. Instead of writing L0x, L1x, L2x expressions, we directly compute numerators and denominators separately. This will make the calculation faster and cleaner. Okay, let me show you. Your D naught. D naught is minus D naught will be x minus x1 upon x naught minus x1. Okay, this type of expressions will be there in D naught x, correct? So you are just calculating this numerator part, okay, this numerator part separately and this denominator part separately, okay. So d naught, the first denominator is x naught minus x1, then it will be x naught minus, this is x naught minus x1, x naught minus x2, this is x naught minus x3. So the answer will be minus 70 here, keeping the denominator separate. Okay, same way you calculated d1, which is x, and this is x1 minus x naught. Okay, this is x1 minus x2, this is x1 minus x3. Clear? So you're getting the value as 30. Same way you calculated d2 and d3, whose values are coming out as minus 30 and 70. Okay, I hope this type is clear. Similar way, here calculating the numerators, the upper part, by putting x minus x1, say it is there, we're keeping x equal to 5 here, then x1, rest of the steps are same. Yes, calculating numerators separately. So first numerator for L05 is coming out as n naught, that is equal to 6. Similar way you calculated n1, n2 and n3. This is corresponding to L15, numerator corresponding to L15. This is corresponding to L25 and this is L35. Okay. So the final answer, you are keeping numerators separately, denominators separately. Okay. The formula here will be for this value. It is actually equal to P5. So it is y0 into, this is n0 upon numerator upon denominator, okay, plus y1 into numerator n1 upon denominator d1 plus y2 into numerator n2 upon d2. Same way last time will be y3 that we calculated, that is given to you, that is equal to 24, and the value of n3 upon d3. This is the final expression that you are supposed to solve. Okay. put the values of n naught, d naught, y naught from either you calculated them or from the given data. You can find the final value to be equal to 15. Okay, so the value of the function at the point 5, that is p5, equals to 15 here. Okay, I hope you enjoyed this video. Thank you.
If you found this video helpful, don't forget to like, share, and subscribe to the channel. Thank you.